Hello everyone! Today I want to present number 6, General Relativity, Sanity Checks and Discussion. And below we have in blue 1 through 5, the links to my previous presentations if you want to brush up on some topics. And I also included number 6, the link where you go there, you get a free download of The Meaning of Relativity, a book written by Albert Einstein himself, the one who came up with all this stuff. And you can get his latest view from 1955, the year just before he died. It's revision number 5. So going on, along the way we've got to accomplish a few things. One is we need to derive this thing called JUV. And what's really cool is this JUV is composed of components that all of us understand intrinsically. So we have an intrinsic understanding of the JUV. And then we have to expose this thing called the Metric Tensor, which represented the same way other people do, other physicists, as J subscript UV or J superscript UV. And they call that the Metric Tensor. It's just a name. As is the J subscript UV being covariant and J superscript UV, or G superscript UV being contravariant. And it turns out that if you multiply the metric tensor in the covariant form times the metric tensor in the contravariant form, this G subscript UV times G superscript UV there, it equals 4! 4! 1, 2, 3, 4. 4 stumps, 4 bananas, 4 apples. 4 fingers. It's very simple but amazing thing, and we need that actually to prove Einstein's gravitational field equation. So then we need to derive the field expression again, but now from a vantage point of having a full understanding of the metric tensor G subscript UV, and we actually derived that before the gravitational field expression, but from looking at physics, and it was a very sort of arduous process, probably something similar to what Einstein went through himself in the first 5 videos that we've done, presentations. And but it was a very useful exercise because you learn a lot, and certain parts of your mind come to the fore and develop, and it's an interesting adventure and exploration of physical reality, really, which some of us do not want to skip. But then we'll evaluate which expression, because we'll be doing a little bit of arithmetic later on, which expression of the few that we come up with that satisfies the conditions of being a well-behaved gravitational field expression. Einstein had to do the same thing because he came up also with a number of very similar expressions, and he had to choose among them or keep going till he had a choice that satisfied all the requirements of physical reality. And this is important because we're doing physics here, and physics is a study of physical reality and creating models, usually mathematical or arithmetic models, that describe the behavior of physical reality. But mathematics in general is not necessarily a good models, doesn't create good models of physical reality. What you have to do is when you create the model, you have to test it and make sure that it's empirically correct and satisfies all the things like conservation of momentum, conservation of energy. Anyway, we'll look into that as Einstein had to do, and we'll derive what we need to know, and we'll make our own best selection. So next we are going to start with the same place that Einstein started, with the Newton's theory of gravitation. Now, Newton's theory works perfectly well for low masses and low velocities. And so whenever we come up with a broader theory that Einstein came up with, it has to match Newton's results under the same conditions of low mass, low velocity. And we're going to actually need that later on when we have to evaluate a particular constant. So it's kind of tricky to say this, but I'm gonna jump around and just get to the end here as quickly as we can. The divergence. Here's what in 1867, what the Newton and the mathematician Poisson came up with, and it's this expression up top there. The upside down triangle dot G is equal to negative 4 pi rho. The thing looks like a P in blue there I put. So in 1687 they came up with that, and the divergence, which is that upside down triangle, listen to this. It is a measure of the total sources per unit volume. The total sources per unit volume, which is basically the way they thought about it was like the perpendicular gravitational flux per unit surface area multiplied by the total area divided by the volume. Now, you can do a screensaver of this and think about it, but it's very simple. This is Newtonian mechanics. For Newtonian gravity, the flux per unit area divided by the volume is equal to the force divided by the unit mass divided by the volume, and that's equal to gm divided by v r squared, where r squared is the radius squared. So that's the flux per unit area divided by the volume. Now the total flux, you got to multiply that, negative gm divided by v divided by r squared. You got to multiply that by the total surface area, because you want the total flux divided by the volume. So that's what Poisson's expression was all about. So, so in this case, the mass or momentum or energy is the source of the field. So we can use the mass density as the flux density. Okay, the mass density rho as the flux density. And below there, I derive it all out. 4 pi r squared, that's the area, times negative gmv over r squared is the flux per unit volume divided by the r squared. And you see here that r squared, I have them both in red because they cancel. And so you get, that's equal to 4 pi times negative gm divided by the volume v. And that's m over mass times the volume v, mass divided by the volume v, rather, is the mass density. So that's equal to negative 4 pi times g times the mass density. Negative 4 pi g rho. And that's the Poisson expression. And we're going to need that later. So you can do a screensaver of this, or just pause it, look at this, and you'll see it holds up. And so from there we move on. Now, this Poisson expression of Newton is really quite amazing, because what it says, you can see I kind of show it again, but it's 4 pi r squared times negative gm over the volume and over the r squared. The r squared is cancelled out, okay? Negative 4 pi times g times rho at the top there. Now, the units of g are meters cubed divided by kilograms divided by seconds squared. And the units of rho are kilograms per meter squared. It's the mass density, kilograms per meter squared. So the units of 4 pi times g times rho, which is the Poisson's expression, the units of those are 1 over seconds squared. Now, if you go back and remember presentations 1 and 2, we have, namely, you can see our geometrical diagram showing momentum in 4 dimensions. Distance and time are both measured in the same units meters. When you throw, as I did, momentum vectors in 4 space, like 2 momentum vectors form a plane, and to get the geometry to work out nicely, you need balanced units. So one balanced unit is to measure time in meters and space in meters. So their time and distance are balanced. And so when you do that, balance the units, then the units of 4 pi times g times rho, that constant there, is equal to 1 over r squared. 1 over r squared. So this constant 4 pi g times the mass density is equal to 1 over r squared. Now, in I think it was presentation 4 or 5, I showed how you measure the curvature of space-time. And doing that for the Earth's surface, we get the units of it are 1 over r squared. So those are the units of curvature. Those are the units of curvature way back in 1687. So if you just look at it, like I'm going to look at it right now, it says, and way back in 1687 when Newton invented this, his Poisson's gravitational expression was shouting, on the one hand side, I am curvature. And on the other hand side, it says, I'm this constant times the mass density. Okay? So the mass density on one side of the expression with a constant is equal to curvature. So way back in 1687 was the beginning of Einstein's, if you look at it, just what the expression is saying, it's already talking about, having mass density on one side and curvature on the other. So it's a particular special case of general relativity. So, and I think that's what Einstein saw when he was really looking at this. That's the beginning of his work, right? Oh, it's relating space-time curvature to mass density. So here I say Einstein in 1910, some 223 years later. It took people that long to be able to look at what's the expression is basically shouting at us. He was the first one to listen and act on this message. He placed the Poisson expression on the right-hand side of the equation. He placed the space-time curvature on the left-hand side of the equation with an equal sign in between it. And in this case, the equality is not like two bank accounts and two people's, different bank accounts that just by coincidence happen to be the same. No, this is an equation of identity. Like the mass density has the same identity as space-time curvature. So so we're going to have more to say about that. And here's, I made a little expression of it at the bottom there, with surrounded in a purple box. 1 over r squared is equal to q, which is that new constant there. That's, 4 pi g times rho, the mass density. So there's Einstein's expression in its most rudimentary form, and you get that from 1687 just by looking at the expression and say, what are you trying to tell me? So anyway, that's a major deal right there, to be able to see that if your mind was so inclined, way back in 1687, you could have started Einstein's work from this very good foundation provided by Newton. Okay, so this isn't the only one that once you start, like, one of the things, let me just say, working with trying to look at the physics and try and not suppress some of the mathematics, and just trying to see what the physical situations are trying to tell you. One of the results I found is that the equations start to basically shout at you what they are, and so we're going to look at this. So let's look at it. We'll think about another thing according to Newton. And Newton said energy is equal to force times distance. That's like work. Force times distance equals energy. And that's equal to mass times acceleration times distance. And the units of that are kilograms, meters squared per second squared. And these are clearly units of like meters squared per second squared. That's like a velocity, meters per second, times another velocity, meters per second. So you get two velocities multiplied together, you get meters squared per second squared. So again, just looking at energy equals force times distance, you get that energy, and then I'm looking at it, it's like a mass times velocity squared. And I say there, these are clearly units of mv squared. So again, looking at the expression of Newton, it tells me that the energy is equal to mass times the velocity squared. Now earlier, using our geometric diagrams, and due to our measurement of the vacuum of in the vacuum of the vacuum capacitance and the vacuum inductance, we demonstrated that all oscillations within the vacuum can travel at only one speed c, and this was in presentations 1 and 2. And that the only changes we detect are changes in the direction of the velocity of these undulations through the vacuum, which is basically everything, and never changes in the magnitude of the velocity, just the relative direction. This means that the speed for everything is the same, which is the speed c. Okay? Thus, the units of energy from Newton are really proclaiming energy equals force equals mass times acceleration times distance equals mv squared, but because the velocity is only one velocity, which is equal to c, it's mc squared. So we have way back in Newton's age, if you just were able to look at it and ask it, what are you trying to tell me? Under ideal circumstances, you see it shouts back at you, E equals mc squared. Now, that in itself is good, but I haven't said the next thing I'm going to say yet, which is c is a velocity. And we have two velocities multiplied by each other, c squared. We haven't talked about the direction at which these velocities are pointing. So that's actually, there's 16 possibilities there. There's 4 directions and there's two velocities. So if you want to generalize that, you end up with a 4x4, well, one of the things you put it in a table, 4x4, 16 components. So intrinsic in that statement, which comes right out of Newton's equation, is basically the beginning of the 4x4 tensor that we need to have, and Einstein came up with for general relativity. It's all there if you just know how to ask the right questions and are prepared for the answers, and don't shut your mind down, you know. So anyway, so we need to explain the meaning and utility of this mathematical object called J subscript UV, in red, J, and G subscript UV, or superscript UV, depending, G subscript UV in blue. And I'm going to show that J subscript UV is basically innate. Humans understand this whether they are taught it or not. And they use it every day. I'll show you that. And also G subscript UV, which could otherwise be this sort of abstract thing, I can show that, and I will, that 2 JUV times JUV with a little tiny thing called transpose, which I'll show you what that is. But basically 2 JUVs, which are intrinsically known to humans what they are and how to use them, are become a GUV, 2 of them. So GUV then becomes intrinsic once you have it explained that it's made of JUVs. You could actually use JUV transpose times JUV and eliminate G subscript UV. And I sort of wish they for the point of simplicity of understanding, just eliminate that. So then it's all intrinsic. So let's move on. So I'm not going to talk about, notice I write a lot on the page. That's for you. I'm not necessarily going to speak all this, but let's say you want a little background or you don't know what I think you already do know. You could you just pause this or do a screen save and read it at your leisure. But right now I want to talk about the invariant. Einstein, people say because he called it relativity that everything's relative, and Einstein showed that. Well, actually, his way of thinking was quite the opposite. He liked to and needed to look at all of the variation in nature, where you have accelerations versus no acceleration. You have curved spaces and no curved spaces, and different perspectives based on how you move with respect to some other thing. And he wanted to see what in the context of all those changing things, what can we count on, to not change. And so what we have here is his invariant for relativity, special relativity, where there's no acceleration, so it's not inert. It'll come to me. It's funny how you get that. Anyways, relativity with no strong gravity and no acceleration, because there's gravity just introduces an acceleration. So we now need to produce another similar metric, invariant metric, which will be true both for special relativity and for general relativity. Now, design engineers, like I'm a design engineer, both electrical and mechanical, a little bit like Einstein, because remember he had something like 20 patents and 85% of them had to do with refrigerators. Now that's mechanical engineering, but he also did electrical things to do with the waves moving through the medium, which is the vacuum, waves moving through the vacuum. So very similar. And he was a design engineer because he designed the mathematics that he needed to create a model of this more general situations where you can have no accelerations or accelerations. So what we need then is to specify what we need, which is in the yellow box on the bottom there. And that is, we need this function g subscript uv such that when you multiply it by a column vector with the 4 components of space and time, dy1, dy2, dy3, dy4, one column vector. When you multiply that by g subscript uv, and you multiply that by dy1, dy2, dy3, dy4 as a row vector, that you get the original invariant that we see above there that was applicable for just special relativity. So we have the same invariant produced now in curved spaces and uncurved spaces. It's a generalization. That's why he calls it general relativity. Now, why are the coordinates, and in the rest of this presentation, when you see y, it's the non-local coordinates, where you are observer in the local frame, where x, x1, x2, x3, x4, those are the different space and time dimensions in the local frame, and y is in the non-local frame. Just remember that. So, and also, it also has to work in local frames where there is curvature. So basically converting one curvature into another kind of curvature. And it does have that ability when we're finished with it. So remember I said that G, which is the blue one, G subscript UV is made up of two J subscript UVs, and J subscript UV we already use and understand very well. So it's made up of JUV. That means I want to, well, since I want to leverage or evoke the new understanding from an understanding that you already have, especially if it's one that's in your bones, like I'll show you that JUV is. Since we want to do that, we want to then show you what JUV is and build G subscript UV out from JUV so that you know G subscript UV, not in an abstract, distant, handed down from heaven way, but in a way that's in your bones, your bones. So here's my specified job for that my specification for JUV. It must take a column vector that it's multiplying and convert it into a column vector in the remote coordinates y, and convert it into a column vector in the local coordinates x. Okay, so when the JUV multiplies this column vector in y, dy1, dy2, dy3, dy4, when it multiplies it, then what you're going to have there, instead of dy's, you're going to have just a column vector in x, dx1, dx2, dx3, dx4. And that will be multiplied over on the left-hand side by the row vector, because this isn't part of that same equation. So the row vector, dx1 times dx2, will multiply the column vector in x after GAUV has done its business with the y coordinates. It'll convert them into the x coordinates, and row times column. Remember, row times column. Did I talk about row times column? How it's just arbitrary? It's a convention, and it's like in the United States, there's a convention that somebody did years and years and years ago. It's going, maybe they tossed a coin. Yeah, I think they did. Tossed a coin and said, we've got to design these roads. Now we're going to drive on the right-hand side, or we're going to drive on the left-hand side. And they decided, they tossed the coin and heads up, that right. So they picked the right-hand side. And so all of the infrastructure was designed to, right-hand turns and clover leaves, and goes on and on and on. The whole system, for its efficient operation, is based on driving on the right-hand side of the road. Now, it's just a convention. In Britain, for example, they tossed another coin, or maybe they tossed some stick or something. The British are a little bit behind. So they have a tally stick or something, and depending which end sticks in the ground, they picked the left-hand side, drive on the left. Now, if you drove on the right in Britain, you'd have a car crash. So whatever the convention is, in this case it's drive on the right-hand side, row column, row times column, RC, row times column. You always have to stick to that. And if you don't, your mathematics will crash. So it's very important, and it's not from, handed down from God or something. This was a totally arbitrary convention, and thank heavens they do stick to it. So it makes everything, the system, be consistent. So anyway, that's why multiply it by row times column. We're going to be doing that quite a bit, actually. So now I want to just show you how JU subscript UV is innate. So what I've done, I want you to imagine you go on a trip through the Middle East. And when you get home, you have a bunch of bills. You open up your suitcase and, oh, darn it, I've got a bunch of bills in 4 different currencies. I've got to convert them. And you go, oh, well, I know how to do that. But I don't want to get ripped off by the exchange rate, so I'm going to work out in advance what I'm expecting to get. So what you do is you look up the currency converters. And actually, I did that just a few minutes ago to update it. Actually, I did it because I made a mistake. I had one of them inverted. Just to be honest, it's kind of funny. So I updated them while I was at it, and so what you have is dollars USA equals dollars USA per dollar pound. I didn't write USA because it makes it too long. Everything on the numerators are dollars USA. Dollars USA for dollars pound times the delta in pounds. Dollars USA divided by dollars reals times the small amount of reals, D real. It's a real amount. You know, you pull it out of your suitcase. But it's a small amount compared to all the reals in the world, so it's an infinitesimal increment, D real. Then the exchange rate for US dollars to dinars times the dollars dinars. That's and shekels time in US dollars per dollar per shekel times D shekel. And then I put in the actual number of, it says up there in red, when you open it up, you got 10 Egyptian pounds, 270 in Iranian reals, 66 Kuwaiti dinars, and 43 shekels. So I put those in the next line there. And I do the calculation on my Excel spreadsheet, and hopefully correctly, it comes out to $246. Now, it turns out that people know how to do this. I've asked probably 20 people, would you know how to do this calculation? And they say, oh yeah, I can do that. I have to just look up the exchange rates. Now, even that is interesting because when you use this in relativity, because they want to look it up because it depends on the time and it depends on the location, which country you're in, what the exchange rates will be. So they say, it depends. I look it up. Now, in relativity, you have to look it up as well. You just have to say at that location and that space environment, what is the exchange rate for these currencies? And it depends on like I said, the time and the location. So very good, what's the word? A very isomorphic analogy, very, very good analogy. So most of you will consider the above calculation to be obvious. And we can represent the home currency as X1 and the foreign currencies as Y, for which we have Y1, Y2, Y3, Y4. And then we can express the currency conversion thing, which we have in yellow on the bottom there. That's how we converted it, how I did it above, actually did it. So you can see in a non-abstract way, which you hopefully you can see that. Then I expressed it more generally. We're just putting in X1 will be the US dollar, and delta Y1 and Y2, Y3, Y4, those are the various pounds, reals, dinars, shekels. And what it is actually, it's equivalent to multiply row by column and add. So again, we're getting that row times column. So if you take these exchange rates, dx1 by dy1, dx2 by dy2, dx3 by dy3, and you multiply by the column vector, you get something different than what we have above. Because I've actually put a more general one where there's 4 currencies there. So because the row above there is just for US currencies. So keep this in mind, because this is the more general version, which we're going to use next. So yes, most of us know how to perform currency conversion, and there's that currency conversion for the US dollars. Now this just gives you the top row of the JUV. We are looking to perform the job of dimensional currency conversion for us. So the top row will put it in, create dx1. But we live, when we're talking about converting the units of dimensions, like spatial and temporal dimensions, there's 4 of them. So it's like we need to convert it into US dollars and Argentina whatevers and Canadian dollars and the Bahamian dollars. So we need to do 4 currency conversions. So we need 4 of these rows. So again, the entire system I'm reading the bottom here is built on rows times column and add together. Okay, I've already talked about that. So go on to the next one there. So you see in the middle, dx1 is equal to, and the currency conversion that we actually used, and I actually calculated an example for the trip in 4 countries in Europe area. And now, but I want to do it for 4 different currencies, like the US dollar, and for the, let's say the Argentinian dollar, the Canadian dollar, and the Bahamian dollar. So I want to convert all of those. I need 4 rows. We need 4 rows. And so we get that block of equations, 4 equations in the middle there, in red and blue and black. Now, mathematicians don't like to write it out so largely. So in such a, it's a waste sink in space on a page, and I don't mind doing that because I want to understand it in my mind. But they want to write it more succinctly, and they use these summations in order to compactify these expressions and make it easier to write. And yeah, so and then they put these kind of horrible looking symbols which represent sums. Looks like a pointy, bitey thing. Anyway, what it is though is just a row, a 2-wheel odometer is what they've created. And a car odometer, which by the way, you definitely know how to read a car odometer. And I think it has four wheels, and it has 10 different 9 different numbers on the wheel. And we have here just 2 wheels and 4 numbers. So it's so much simpler, but it's the same idea. You notice on this expression here that all of the d whatevers on the top, dx1 for example, all the way across, it's dx1. And then you go to the next one and all the numerators have dx1. dx2, all of them have dx2. It's the second row. And then on the third row, it's dx3. So it's a row counter for the delta x's. And then on the fourth one, it's dx4. But notice all the denominators. That was for the numerators. Notice all the denominators are in, row. Sorry, yeah, row counters. They're all 1, 1, 1, 1, 1, 1. Next one over, 2, 2, 2, 2, 2, y 2, 2, 2, y's. Next one over, the denominators, y3, 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 y3. Third row, next one, y4, y4, y4. Fourth row. Now, we, the top row there, we already understand how to do that innately. Everybody knows how to do that. So the top row it's written in symbols, but other than that, it's exactly what you already know. You already know this, the top row. And if you go to the next row, it's just for a different currency, like Argentina. So you know that one as well. And the third row, I'm just putting in a different currency conversion, x with a x3 for the third currency. Okay, so you know that one as well. And the fourth one, just another currency, the dx4. You know that one as well. You know this whole thing. You know this whole thing. So now let's just perform. I haven't talked about. I talked about the first term, and then it's multiplied by dy1. And look what the dy1, what it does. And remember, we did this with a real example. With a real example. So right there, dollars USA 1.38 times 10 per pound times 10 pound. Okay, and you get the answer. So here, that delta D times Y1, for example, in the top row, the last part of the first term, that's the amount, like $10 in the first currency one, and in the first currency, and then D2 is the amount in the second currency. D3 is the amount in the third currency. So you know how to do this. You know how to do all of this. Okay. Now, what we have to do again, and it's bad enough to convert what we already know into these 4 rows, but it's not too bad. You can understand this very easily, because you already do it. Now, this row column 2-wheel odometer thing on the bottom is a short form of this. And what you see here is the it basically reconstructs all of the. Now, if you look at all of these terms, that's all it does. Column counter, dy subscript 1, okay? That's at the top. Column counter. The column counter is this first summation here. So it's going to be dy sub b. It starts out as 1. And delta x is 1. So delta x is a row counter, which is the numerator of it. So delta x1, delta, So it starts out, row counter goes to 1. And then the column counter goes 1, 2, 3, 4. So you can see here, the row counter is the denominator, and that last term that multiplies. So it goes dy1, and then on the other side, just beside it, times dy1. 1 is del, so let's call it del. Del y1 times dy1 there. And then it's y1 across the whole thing, while the column counter goes 1, 2, 3, 4 along the top row. And then the row counter is updated to number 2. So you get delta y2, del y2, del x2 rather than the top, and you get that. And while the column counter goes y1, y2, y3, y4 goes through its permutation. So it's reproducing those four equations. That's all it's doing, this summation. And you'll see that in relativity online or in books is worse than that. I'm showing you the sort of assembly code level of how it works, and then I'm showing you the contraction here. It's a convention to leave out the summations, right? Can you imagine? So it's really, I'm showing you how the summation works, and I'm also showing you what it means, even that. But the degree of abstraction is not even done yet for what they do. But I'm not going to do that to you. I'm showing you the whole thing. Okay, so we move on here and say, okay, J of V equals this thing. It's a currency converter for four currencies. It does the for the 4 dimensions. So it's the same as what we did for the 4 countries, but we want to convert it into 4 currencies. US currency, Argentinian currency, Canadian currency, Bahama currency, as an example. And you take the 4 European currencies and convert them into those four currencies for whatever reason. So now, the job that remember I said we create the specifications and then we design the, I'd like to call it arithmetic just so we don't get too intimidated by it. Design the arithmetic to perform this specification that is on the line below. It must do that. And then we can check that it does it. So we've got J subscript UV. We have it right there. It's right there. See, J subscript UV equals. And those are all the currency conversions. So now we need to test it. Let's see if it actually performs its function. Okay, so now remember row times column. I keep going on and on. That is the convention. So we have to follow that. So we take the first row here, and the orange, see that orange arrow? And there's a red arrow too. But I want to operate on the row. Row times column. We have a column of the column vector, dy1, dy2, dy3, dy4. And that was part of the original specification, you'll see. See, right there. I just moved the chart back. See that red arrow? And see what's next to it? The row vector, dy1, dy2, that's part of the original job we gave JUV. It must do that for us. So now I'm looking at to see if it actually does it. There's the column vector again, dy1, dy2, blah, blah, dy4. And here's the row of JUV. And we're going to multiply row times column. And so what happens when you do that? You get the first term, and add, right? Row times column and add. So dx1, del x1 divided by del y1 times d, which is a small increment, y1. That's a currency conversion. You're used to that. You know how to do that. Then that gives you, d, delta, d, the increment, x1, dx1 as a column. First term, d, not del, dx1, okay, in the column. It's building a column vector. Now you do the same thing. I could move that orange arrow, but I won't. Del x2 divided by del y1, del x2. So like, notice it's on the second row, so the numerator is all 2, 2, 2, 2. And then notice on the numerator in the third row is all 3, 3, 3, 3. And notice how the denominator is D1, 2, 3, 4. It's a column counter, okay? So anyway, we do that again do that. Row 2 times column, right? Row times column. So you get del x2 divided by del y1 times dy1. And it gives you dx2. dx2. The amount of x2, you've converted that currency. So you created dx1 from the first time you did that. Now we got dx2 in a column. Then you do it again for the third row, and the first term, when they're all the same, they do the same sort of thing. You do this, and you go and do times dy1. It produces dx1. dx3 actually. All three of them contribute, like in your suitcase when you converted them. Each one gets a little bit of a amount of US dollars, and you get the total amount of dollars. So you get d, when you do that one on the third row times the column and add, you get the, and add, that's the point, they're all additive. You get dx3 in a column. And then you do the fourth row times the column again, you get dx4 as a column. So what you have is the row dx1, dx2 in the center there, times the column, you get squares. Row times column and add. dx1 times dx1, dx2 times dx2, dx3 times dx3, dx4 times dx4. And in this case, you get, if you take a row vector and multiply by a column vector, you get a row vector, dx1 plus dx2 plus dx3 plus dx4. Because row times column all goes into the first component and adds, so that you get a row vector. So, and that's the red arrow. It works. It produces a row vector, dx1 squared plus dx2 squared plus dx3 squared plus dx4 squared. That's row times column and add. That you see there are the additions. So the expression is for curvilinear space, and it works down to pseudo-flat space. It works. We just tested it, and it works. And at the bottom, I just reiterated the result. That is the result. So this thing that you see and you understand the components of, you understand that, and we checked it, and it works. So we have JUV. So J subscript UV is under our belt at this point. Okay, we derived JUV as an extension from what we already knew. For example, we already perform a form of JUV whenever we perform foreign currency exchanges. We also do it whenever we go into a shopping center. We do something very similar. You got one currency in this case, and you do a currency exchange for the transaction of converting dollars into apples, dollars into milk, dollars into pizza crusts, whatever you're buying. You're doing that every day. So we derive that. From this new vantage point, we are positioned to fully perceive the relativistic field equation down to its core in all its simplicity. We are in a position because, remember, I'm going to show you next that G subscript UV, the blue one, is made up of two J subscript UVs, which you already know. And you do already know it, but maybe you have to do screen saves and read it a few times and go through the text. You know, you still have to get used to it, but you already know it. Yes, so what we have here is conversion of this column vector in the remote coordinates using the JUV plus the addition of a row vector in the local coordinates. And notice that this formulation, on the right hand side, we still must supply vectors in both terms of x of n and y sub n. So the local coordinates and the remote coordinates. So that's mixed coordinates. And so, but it does a nice job given what the inputs are. And the JUV times the column vector in delta y, dy's, dy1, dy2, etc., dy4, produces a column vector dx1, dx2, dx3, dx4, which when multiplied by the row vector in the local coordinates produces the invariant. But what we want to do next is we want to convert this row here to a row vector with the same dy1, dy2, etc., dy4. So the question is, what do we have to do to this function, this Jacobian function here, in order to be able to have it operate on, instead of dx1, dx2, dx3, dx4, have it operate on dy1, dy2 plus dy3 plus dy4. So that's the question, and we're going to design a new function here. It's not going to be JUV, it's going to be called GUV, UV. It's that blue thing, blue script. And we're going to design that and build it. So let's do that right now. So moving on. Yeah, so I've just said here, what we want to derive ultimately is this, the invariant is equal to the remote function g times the remote invariant that applies in the local coordinates, well, the remote coordinates. Yeah, so with the variant in the remote coordinates, it transformed. So we'll see what we're going to produce that. So, and there's something a little bit funny in here. I mean, humorous, because we already have this here. We already have the Jacobian. And we're trying to modify it so it can take these inputs here and produce the invariant, same as the local invariant that we're used to, but using the non-local coordinates, which might have a lot of curvature in them, and huge gravitational fields, and large velocities, relative velocities. So applying in the more general case, that is, and it might even apply between one with a lot of high velocities, high gravitational fields, and then another area from perceiving in that other area, which may also have high gravitational fields and high speeds, but different. So it can convert anything. That's being fully general. That's what we're going after here. So what becomes apparent, and it's kind of funny, because remember I was talking about how the whole system, the system of modeling, it doesn't come from on high in heaven or anything. It doesn't come out of nature. It's actually, we manufacture this to do a particular job. And as part of that job, same with the highway system, you have to have a rule so you can build everything around a certain kind of behavior. And the kind of behavior is, when you multiply these things, do it row times column, not column times row. Row times column, and not just some of the time, row times column and add. In every case, don't change it. So here we have this Jacobian function here, and it's actually a matrix, but here, now I'm starting to fill in the description of it. And this one right here is actually, to make it work, we can't put another Jacobian in front, because row times column won't work with that. So, but we actually need to, if we could, and say, oh, on this one, break the convention, and just for this one little one, do column times row. It would have been great. But they can't, the powers that be are terrified of this. So instead of that, they do something else. If you switch the rows in the Jacobian on this new thing, G subscript UV, well, that's not part of it. If you take the rows and put them in the columns and swap them out, rows for columns, so you actually change out this matrix and swap the rows for columns, then you're doing the same as multiplying by columns times rows rather than the usual rows times column. So to accomplish this objective, you have to create this new animal here, where you've swapped, see this row here? That becomes the first row becomes the first column. Second row becomes the second column. You can check that out yourself. And when you do that, they came up with a nice name for that to hide the sort of this kludge that they've created here. They call it the transpose. So we're going to use the transpose here to accomplish our modeling objective, which is to perform this conversion now. See here in the equal sign, and we're on the right-hand side of the equal sign. Here we have the non-local coordinates and delta y as a column vector, and here we have the row vector in delta y now, not in the old delta x. We have it in delta y, And when you do the row times column, you see here, like this, let's look at the first term. It'll be dy1 times this del x1 over dy1. It converts it into dx1. But the conversion is done inside this multiple, these two matrices multiplied together. So it's converting it. It starts out, see, the coordinates are totally, I've lost my arrow again. Let's make that thing on top. Kind of funny. Arrange, put it on the front. Yeah, now I got my arrow back. That's good. So these are the non-local remote coordinates here, and they're on the other side here, the non-local remote. And this is a function. It's the Jacobian, and the trans-Jacobian with the row and columns swapped out. In other words, the top row, the first row becomes the first column, second row becomes the second column. Very, very simple conversion here. But these two together, multiplied together, the Jacobian transpose times the Jacobian, is this GUV thing that we've been looking for. Because when you multiply this over here, you get it in X. You get the row vector in X between these two, which we want. And when you take starting out though with the foreign coordinates, and when you take the row vector here from the foreign coordinates and multiply it by the transpose here, you get a row vector in X. So when you do this, you get a column vector in Y, and when you do this, you get a row vector. See, the outcome here is D from this complex here. This two Jacobians, one Jacobian transpose and the other is a straight Jacobian. The outcome is you get a column vector here in X, and you get a row vector in Y. Starting out though with the remote coordinates in Y, in a row vector and a column vector in Y. So it performs this conversion that we wanted. That's our specification, is to have it do it, and it works. So what we write when we want to write this down, we say s squared, which is this s squared is equal to dx1 squared plus dx2 squared plus that's the s squared, not the primed s squared, is equal to this, And here, see this GUV, Jacobian transpose times the Jacobian. And over here, I have GUV because of the same thing. GUV is equal to the Jacobian transpose times the Jacobian. Not one thing more, not one thing less. Okay? It's that simple. Now, so we get s squared is equal to dx. Okay, that's what we have. We need to prove now that, because this is kind of, actually, I like this view of it. I like it, even though it's a little bit ungainly, because see here you got a row vector, and then you got and then you got the GUV in the middle, and then you got a column vector. And what people want to say, mathematicians and people like Einstein, they want to say, here's the local invariant, and it's going to be equal to the non-local invariant transformed by this GUV function. And that GUV times the whatever local, which might be remote, invariant is going to always equal the our local, the laboratory that we have on Earth, invariant. So that provides the invariant for general relativity. And now we have to prove that what we have here is the same as rather than having a row vector on the front and a column vector at the back, you provide the multiplication of these two to get your s prime squared, your s squared in the prime reference place, and multiply by g of v, and you get this primed in our local coordinates. So it's hard to paraphrase what it is, but when you look at what we're really talking about, it's very, very clear in every case. So yeah. So here's what we've basically done. S squared is equal to, and these two row vector g of v and times the column vector. And they want to say, oh, can we put this one over on the other side of g of v so that we have the s primed invariant, and then we can make it look really sleek, like s squared is equal to g of v times s in the primed reference frame. So we're converting across from the prime reference frame into the R units. So let's move on and see. Okay, oh, click out of this. Yeah. Okay, so this is just an interesting. I want to show you that these, like mathematics, we're building models, and I want to show you another way of thinking about G of V. Now you can express it here as J transpose times J G of V equals that, right? But we can also express it in a way that we're not going to use that much. But we can express it by this. We take the rows of here of the J of V transpose. So we want row 1, row 2, row 3. I'll do it with the arrow. Row 1, row 2, row 3, row 4. And we take the columns of the Jacobian function, the regular Jacobian function. And remember, we switched columns and rows, so they're going to be the same thing. Like if you look at it, notice here that they're the same, they're the same, they're the same. So it's basically, it's the columns of the J transpose. But really, you could just take the rows twice, right? Take the rows of J of J transpose, for example, and you multiply them in the ordinary way, which is you take this row vector and you multiply it by itself, and then you take this same one and multiply it by the next one over. That's ordinary multiplication. Take this one and multiply it by that one. Take this one and multiply it by the last one. And then take the second one and multiply it by the first, second one, multiply it by the second above, second one, third, second, fourth. I'm going to jump to the last one. Take the last one and multiply it by the first one. Then take the last one, multiply it by the second one. Take the last one below and multiply the third one. Take the last one on the below, multiply the fourth one. Do an ordinary multiplication. That is the same operation as taking J transpose times J subscript UV. So row times column is basically simulating an ordinary multiplication. So I just maybe want to pause that, and we're not going to do it here, but pause and have a look at it. It's just an ordinary multiplication. So there's more than one way of expressing the exact same thing. And people, I guess people like this row column thing because it's more compact, and then ultimately they don't want to deal with these big blocks of matrices either. So they just they make up notations that contract it into a number of summations. Oh, and worse than that, they don't show the summations even, and it becomes an arcane thing where if you didn't have it explained to you by a professor somewhere, you might not ever know what the heck they're talking about. But it looks nice on paper, but it doesn't show any of this stuff, which I'm showing you right now. The heart of it is what I'm showing you. So I'm looking at this. I have to remember what this means and why I did it. Oh, this is marvelous. What I'm doing is we've proved. I'm going back to this one. We've proved. Let's go back to this one. One more. We already showed that. See this one right here. This line. We showed that s squared is equal to if the row vector in the remote coordinates times g of v in the remote coordinates times the column vector in the remote coordinates. So the whole thing's in the remote coordinates, but it ends up back as our local invariant. So this expression is invariant. It doesn't change. It always gives you that s squared, which we're familiar with, our local invariant. So and then on the bottom here I say we need to prove that s squared is equal to g subscript uv at s squared in the prime coordinates. Now, do we need to prove it? Well, other people in the industry or the academic industry like this one because it says you take the invariant from in the prime frame, and you multiply it by GUV in the prime frame, and you get the invariant that we know and love, and it becomes a universal invariant. So they like this form. So but I look at it, we proved this form here where you got a row vector in front and you got a column vector behind. How do we know we can take this row vector here and move it over and multiply the column vector? And you've changed the order of operation of this thing. And that can be a no-no in mathematics. Like, you can change the associative properties if you can play around with this stuff like I have. And you find out that as long as you multiply this first and then this second and this third and this fourth, you can do that's going to work. But and you can take this group and multiply them together, and you take this group and multiply them together, and then multiply this first group by this second group. In so doing, they call it the associative property. You haven't changed the order of anything. It's still this one's first, this one's second, that one's third. But you can do it in groups first, and group here second, and it just doesn't mess up the order, and that one works. But to take this row vector here, and stick it in the back and multiply it by the column vector, then you've changed the order of the operations, and I get nervous. So we need to prove that, mostly because it really, I find it very unsettling, so I have to try it out and see if it's true. So let's do that. I gotta go too forward ahead, I guess. Okay. Take me out of here, Scotty. Beam me up, Scotty. There we go. So that's not I've already talked about that one. This is the one. So now I'm going to try to prove that. So what I do is I want to calculate G11. And I do that here, row times column, where this is J transpose, this first one here is J transpose, and this is J, the irregular Jacobian. So I have here G11 is equal to J transpose of this. So, and then I work it out. G11 is going to be row column. I'm going to put that in the top here. Right? Bring it to front. Should have done that in advance. Okay, row times column. And what you get is down here. This times this, plus this times this, plus this times the third one, blah, blah, blah. So you get this, and notice they're all squares. because they're the same in the both terms. Each of them. Okay, so G11. What else do I need to say? So yeah, so I just show S squared prime is in the prime frame is the this square and that square, dy1 squared, dy plus dy2 squared plus dy3 squared plus dy squared. No surprise there. G of v times s squared is, here's all I did was I said, okay, it's g, so it's going to be, using the old rules, g11 plus g12 plus g, row column again, right? Remember, row column. And then you go, oh, row number 2, column 1, column 2, column 3, column 4. Row number 3, and all the row, this index is all for 3, right? But row 1, 2, 3, 4, row column. Row 3, column 1, row 3, column 2. Row 4, column 1, row 4, column 2, row 4, column 3, row 4, column. Okay. So now, what I did here, it's kind of cool. I just looked at it. Remember equations start shouting? I've described that to you. So this is kind of neat because I look at this and it's row column. Row times column. See here, this is G, the G matrix, GUV, which is these two multiplied together. So that, and then these two multiply by s squared. So, which is this, s squared in the remote coordinates is this thing. And this transpose, very important. If you look at row times row, it doesn't make any sense, but transpose means swap it and turn it into a column, right? So this one, what it means is dy squared plus dy1 squared plus dy2 squared plus dy3 squared plus dy4 squared. Okay. So now, when you take this matrix of G and you multiply it, remember it all comes back to this thing again, over and over again. Row times column and add. So you take this row here, the top row, and you multiply it by this first column. It only has one term in it, dy1. Okay. So, but it only has one term, so only G11 gets to multiply in this. And then when you do it again, second row, only the top one gets to multiply, etc., etc. You can do the multiplication. So what you get for G11, okay, what G11 incidentally is that, I think I told you that already. So you're multiplying row times column. So row times column, only G1n can make contributions, only G1n. So only the first, every time you do the row, see this is just a row vector. And we're going to multiply the first row times this first row here times this column, and then you're going to multiply the second row times the next column for the next component on the top. Third row times the third column. So in every case, only the first row can contribute. So that's the first filter here. So we don't have to think of all these term 1, 1, 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, etc. 4, 2, all the way over to 4, 4. They don't get to contribute in this system that we just have created. Only the first column. Okay, that's the first filter. So we don't have to worry about these last three columns. Yeah, just the first column. That's the first filter. Now, mismatched double indices produce multiplicative, 0. So when you multiply anything by 0, it's 0, right? In the row column, I say RC in this context, I mean row column. multiplications in all the resulting terms. So mismatched double indices. So unless the indice is the same, you'll have this zero, because it'll have a zero contribution on one of the things that is multiplying, and it cancels out. It wipes everything out except the matched indices. For example, if you're converting, if you have the conversion in, let's say, Canadian currency multiplied by the conversion in U.S. Currencies, and you only have U.S. dollars. Now this is a weird situation, but mathematically speaking, so it'll convert the U.S. currency, but then on the U.S. dollar portion, it gives zero. The multiplication is zero because you don't get anything back from Canadian dollars from a U.S. Currency. So you get zero times the U.S. exchange amount, and zero times an amount is zero. So you have to have the same indices. So and that's filter number 2 here. Filter number 2. So filter number 1 and filter number 2 only leave the first column with matching indices, and there's only one of those, and that's G11, and we know what that is. Isn't that beautiful? So just by looking at it, we're able to see right to the heart of it, and just ghastly reduce the number of possible options of what can be in the resulting answer, right? So now that's pretty exciting. So only G11 can contribute. So if you take this multiplication, this is G11, remember? I worked it out. So there it is. And you take G1 and you multiply it by this first row vector here, which is what you need to do. This is, by the way, I gotta get my magic wand here. This d1 plus dy2 plus dy3 plus dy4 times dy1 plus d. That's the and this is a transpose. So you take this and you multiply by the column, so you get all of them squared. That's s squared in the primed or remote coordinates. That's s squared. So and this is the only part of this GUV that can contribute in this multiplication. So what we get from that is dy1 squared, because you're going to multiply these together, dy1 squared. Or you can do it once and then do it again. But in either case, you get dy1 squared, and if you multiply that across all, it multiplies across all these 4. And you end up having dx, you get d, not delta. You get dx squared plus dx1 squared, that is, plus dx2 squared plus dx3 squared plus dx4 squared is the multiplication. And I show that down here. And that's equal to s squared, right? Our invariant in our local coordinates. So we're actually there. We're actually there. Because y2 doesn't do anything, y3 doesn't do anything in this expression. So it's actually GUV times s squared in the prime reference. So I gotta move that up. Okay, let's do that. Boom, there we go. S squared 1 in the prime coordinates are invariant in the prime coordinates, the remote coordinates, is equal to this, because these other ones can't contribute because they're for other currencies than these currencies. So that equals dx1 squared plus dx2 squared plus dx3 squared plus dx4 squared, and that's the invariant in our local frame So here's that expression. That's what we wanted. And we got it. We got it more or less just by looking at it and using our brain and not letting the equation talk to us. And we didn't have to go through and, calculate every, and, say that one's 0, that one's 0. It would be a real messy thing. I didn't want to put you through it, but we did it just by looking at it. So we've just proven that the invariant in the local frame is equal to G subscript UV, that's the metric tensor, the covariant version, times the invariant as calculated in the remote location. That's what that little prime signal means. So this is how we can keep, as long as we express it as GUV times the invariant in whatever frame, then it'll be S squared. So it'll be a true, and that it'll be invariant in this form for all the situations that we encounter in general relativity. So we started out by performing currency conversions that everyone already knows how to do, and ended up producing Einstein's general invariant for gravitationally curved spaces, all the way down to flat spaces. So there we have it. So, yeah, this is what we remember. I said earlier. Here I wrote it down. G subscript UV times G superscript UV equals 4. Now here I have. It's kind of like, I don't want to say intelligence test, but it's like, it has that kind of air to it. And like many of these kind of things, it's because it's a logical proof. I created this proof, and because it's like a logical proof, if I talk while I go through this more than a minimal amount, I'm going to be distracting you. But I'm going to just show you what it's about, and then afterwards you're probably going to have to pause it yourself, or maybe do a screensaver or something and look at these, because it's kind of like when you put a drop on a waxy cloth. It's sort of, the drop sits on the cloth. That's what the brain is, kind of a waxy cloth. And then it sits, and then suddenly the surface tension is broken, and the water goes in. That's what this thing is like. So you might not get it right away, but I want to show it to you, and hopefully you'll get it within. You might have to read it 5 or 10 times, which is no big deal, to get something so cool. You'll see it's very cool. Okay, so I have here this Chronicle delta function. Now, it's like, oh, did God make this function that it's when the two indices are the same, it's equal to 1, and when the two indices here at top and bottom, when these two indices, well, the indices top and bottom, whatever they are, if they're the same, it spits out 1. And it's like, wow. No, let me say this. No. This did not come from nature. This is just the same thing we've been doing all along. We make it up. We can make it so it spit out 2 or 4. Or you can make it so it only does it on the even ones. We can make it whatever we want in mathematics. So anyway, that's what this symbol means. So you multiply that, and it means, what it says here is that when U is equal to W, let's say, actually, see, I have to think, because it's a mathematical, logical thing. When U is equal to W, then it's equal to 1. So then it's 1 times W, and it's equal to Q sub U. Or when W, better yet, that's probably wrong. U is equal to W, it's equal to 1. No, then it would be Q sub W. But when W is equal to U, so you got U on the top and U on the bottom, then it's equal to 1. And since U is equal to W, then it's equal to W, and then you have Q to the W. Well, that doesn't change. But u is equal to w, so you can just as easily write that as q to the u, because w is equal to u. So yes, this first line is true, okay? Second line. So when you have a lower indice and an upper indice like this, especially with this metric tensor G, they basically, this V on the bottom, what they call is reduces it. So boom, boom, it's gone, all right? And the W on the bottom, it adds another derivative to the situation, which means that it's G sub W on the bottom, and then the V is gone on the top, so it's UV. And then times Q sub W, it means that W that's on the bottom there, you have to work it out longhand to see it, then lowers the indice, or basically cancels it in this case, above again. So you end up with, but the U on the top raises the indice as U on the QW, and you get Q sub U. So sorry about that. Again, you have to sort of look at this, but the net result is this expression is true. Now, see this one, GWV. Okay, that's great. This GUV times Q to the W. This is equal to up here Q sub U. Okay, so Q sub U here and Q sub W there. So what it means here, you can see this one here, GWV times G superscript UV, and multiplied by QW is equal to Q sub U on the top, or QU on the top. Okay. Well, here we got QU on the top is equal to delta, the delta thing, times Q sub U. So that means that GWV and G superscript UV is equal to delta U sub W, okay? Which means you can substitute them whenever you want. So here's that says it in this last line here, okay? So there, wow, that comes out. It just came out of this thought process. Again, you want to sit down and read this over yourself a few times and have your own brain do these aha. So, and often it takes a few times through to see it from a purely logical perspective. So, and this thing spits out a 1 whenever the indices match, top and bottom. So we know that it's the indices on a matrix. They're like 1, 1, 1, 2, 1, 3, 1, 4. 2, like row 2, 2, 1, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 3, 2, 2, 3, 1, 3, 2, 3, 3. So we notice on the diagonals, they always have the same index. So in every one of the diagonals, it's going to spit out a 1. And there's 4 terms because it's 4, but these indices are all 1 to 4. So you can represent this as as G, this times this, G subscript UV times G superscript UV is equal to the delta, what do they call it? Chronicle delta function. Okay, and we represent that with the subscripts U and V. You got V, it's basically row and column. And then the column vector, row column, goes from 1 to 4. And every time you go 1, 2, 3, 4, this row, because you're going across the columns, and every time you get to 4, the fifth one, the second tumbler, like in your car odometer, goes from 1 to 2. and then you go 1, 2, 3, 4 on the row columns, and then the row you go to the next row, and it goes from 2 to 3, 2 to 4. So anyway, it produces this, and the sum of it. See, there's a 1 here, and then another 4, and then another 1 again, where the indices match up, and then 0, 0, 0, and then going down this diagonal. And the total of this summation is 1 plus 1 plus 1 plus 1 equals 4. So we've just proven, here it is, we've just proven that GUV subscript times GUV superscript equals 4. Yeah, and this, a lot of mathematicians, I've looked on the, I do quite a bit of Google searching, and you almost never find this what I'm just showing you. In fact, that's why I'm desperate. Well, I like to do it anyway. I'm a design engineer, so I want to design it myself, but I want to check it out. It takes forever to check it out. I end up inventing the thing, and then I go on search, and I put it on images, and I look for the image that matches, and I go, oh, that's what that thing is. They call it a Jacobian. Oh, that's interesting, So that's how then I can go and look up Jacobian and find out more about it. It's typically how it works. But I noticed I was trying to find, if this GUV, if it equals 4, GUV subscript times GUV superscript, if it equals 4 just in Newtonian space, or if it's a general thing. And I looked and I saw many, many learned professors that write about it, and they get right up to the point where any reasonable person would say this works in a general space, but they'd have it in such a way that they'd weasel their way around it, and they wouldn't actually commit, because they probably weren't 100% sure. And you don't want to say something online where you're not 100% sure. Although it's not a bad thing to do. You go back and fix it. Have a little courage. But anyway. So I have to say here, I'm going to help out. This expression for curvilinear space also works down to pseudo-flat space. The expression is fully general and is not limited to some Newtonian approximation. Okay, I'm trying to make it clear for everybody out there. And I just hope to have it that I'm right on this one, I got my neck stuck out so far, but I think I am. I think what I say is correct. I'm almost 100% sure. And besides, with science, it's only true. These models, humans create models. And I don't care what model it is. It's only as true as the depth, all the things that it includes and things that it doesn't include, and its scope. What's the subject matter? Does it cover everything, or what does it cover? Where does this model apply? So everything is true within, in a good model, within the depth of the model and the scope, and not beyond that. So now let the real fun start. We've already gone through and we've explained this function. They call it the Jacobian, J subscript UV. And I showed that you already know that. It's deeply understood. It's in your bones, so to speak. And showed what it does and how we can use that. And then this other function, which they call the metric tensor, G subscript UV, the one that was in blue, we showed that is made up of 2 of the Jacobian functions, which or matrices, which you already understand. So, which means that in addition, you already understand this metric tensor. And then we showed what it did, and we actually defined what we needed it to do and proved that it did it. So with that under our belt, we can go on and have the fun part, which is to derive Einstein's gravitational field equation. Hopefully it should be like a piece of cake. Well, let's find out. So moving on here. So let's start with sort of the Newtonian expression right here, number 2. The curvature, scalar curvature, is equal to k, a constant, times the scalar mass density. Okay. So now then we multiply both sides by g subscript uv. And what that does is it turns a scalar into a tensor. And the UV's on the bottom here, so it's a covariant tensor. So R subscript UV then is equal to K times T subscript UV. So that's equation number 3. So now since R subscript UV is equal to K subscript UV, if we subtract one K T subscript UV, we get 0. Subtract yet another K T subscript UV, and you'll get a negative K T subscript UV. Okay, and that's what we see on the right hand side here. Well, since RUV is equal to K subscript UV, when you subtract 2 of those, well, you got to subtract 2 of those on the left hand side as well, and they're equal to R subscript UV. So 2, you have to subtract 2 R subscript UV. Now this is pretty simple stuff. I mean, just look at it for a sec. You can pause it. I haven't said it. It's kind of it's almost grade 1 arithmetic. So yeah. So let's look on going to that takes us to expression 4. Now expression 5. Can we say that if we had minus a half, see, where do we get the minus? Oh yeah, 2, minus 2. Would you agree that minus 2 is equal to minus 1/2 times 4? Because a half times 4 is 2, last time I checked, okay? So minus a half times 4 is going to be minus 2, okay? So in equation 4, we have minus 2 times R subscript UV. And that then the minus 2 is equal to minus 1/2 times 4. We just proved that talking it through. So equation 5 then derived from equation 4 is minus 1/2 times 4 times R subscript UV. And that's the only thing I changed, but I didn't really change it. I just put in something that's true. Now, here's the beautiful part. This is amazing. Okay, look, there's a 4 there now in equation 5. That blue 4. Now we already proved that G subscript UV times G superscript UV. Oh yeah, G superscript UV is equal to 4. So let's put that in there. G subscript UV times G superscript UV, GUV, and replace that 4 with that. Okay, so there we go. And we got equation number 6. Now, which is actually the same as equation number 2 up here. It's amazing. So let's now see. We got basically here. Let me use my arrow. We here we have this G superscript UV, and we've got it multiplying R subscript UV. We can choose to do these 2 operations. Okay, and what happens is with G superscript UV and G subscript UV that it reduces it because the upper subscripts and the lower subscripts act as if they're canceling. So we end up with just R, the scalar tensor. Okay. So then we can look at this. What we're left with, we get number 7 from number 6. A very straightforward way. And then we look at that. And then we look at way over here out of Einstein's book, The Meaning of Relativity. And the version I like is the 1955 version, his final revision 5. And we get this, the same expression if you look at it. So we basically derived it, which is kind of cool. Kind of cool. So in the bottom here, I say, using Einstein's own compact notation, we arrive at his gravitational field equation. I wrote it again there. It's equation 7. All right, so let's move on from that. So it was kind of neat what we just did. We went right through it like almost like nothing. Once we understand JUV and G subscript UV and superscript, the basic metric tensor. So let's see, where do we go now? We want to test the last result to see if it agrees with Newton's result for low mass and low velocity. What we're trying to do, notice I've used just the constant of proportionality, like in this equation 1 right here. I'm going to use my magic wand again. Let me see if I bring that to the front just in case. Bring it to front. Yeah, there. Now I can move it all over the place. So equation 1, R is equal to KT. See, we've been using that, but we haven't defined what K is. All right. So let's do that right now. Start with our equation again. R is equal to KT. And then in equation 2 from before, we have this one here, R minus 1/2 to UV. Now that one looks familiar. That's basically Einstein's gravitational field equation right there. But I'm gonna just do something very simple. See this 1/2 times GUV times KT. Well, KT is equal to R, right? So I made that substitution in there. Now we're going to take this one here, negative 1/2 GUV subscript UV times KT, and we're going to, KT standing in for R, that is, we're going to take that and we're going to move it over to the other side of the equation. In other words, we're going to add this term to both equations, sides of the equation. So we get R subscript UV in equation 3 minus K times T subscript UV plus 1/2 times GUV times KT. So we get equation 3. And you see the red arrow there describing exactly what we did when we moved it. And we had to change the sign as it went to the other side of the equation. So this is standard stuff, very easy. Now, then we want to now find out, now that it's in this form, we want to find out what this K is. And remember we started, I said Einstein started with Newton, because when you're dealing with, first of all, you want to find out what K is. So you say, where in this range of general relativity, which is sort of new at the time that Einstein did it, he wants to find out where do we know enough to find out where K is, and we know for sure. And it's like, well, this general relativity has to work all the way down from low masses and low velocities like Newton's world, all the way up to high masses and high velocities, which is the sort of world of general relativity, at least the full scope of general relativity. So take it down to the Newtonian scope, and then we already know, because of Poisson's expression, we know what the curvature was for that situation. So here we have, I've expressed it now, I've said equation 4, when we take it down to Newton's situation, he only considered, for example, in the Earth, he only considered the mass of the Earth as in Poisson's expression. So, and that's the mass of the Earth, mc squared. It's the first term in Einstein's tensor. So it's R, I like to go 1, 2, 3, 4. And in this expression, they like to call it R00, like the first. So it's just this index notation. Don't worry about it. Same kind of thing. 0, 1, 2, 3 is the same as 1, 2, 3, 4 in terms of keeping track of it. So for this part of, let's talk about R00. Okay. So which is R11 and what we were just talking about. So R00 is a Newtonian case. And that's equal, because of, as Poisson worked out, is equal to negative 4 pi g times rho, the mass density. And so I put that in there. I haven't put the, yeah, I did put the value in there. And that's equal to kt00, the mass density, plus 1/2 kt00. Okay. So, and we know what that is. Again, it's the mass density and the mass density. So we just substitute that in there. Now, it is true that, look at the left hand side of 5. If you take negative k times the mass density and you add 1/2 of k times the mass density, you get negative 1/2 of k times the mass density. Just think about that for a second. Minus, let's just take -1 plus 1/2 is equal to -1/2. Okay. So this equation 5 is true. And if we look at the left-hand side, it says that -4 pi g times rho, the mass density, is equal to, way over on the right-hand side, negative 1/2 k times rho. Okay, now on both sides, both the far left and the far right, you have times the mass density. Well, cancel the mass density. Okay, so now it's gone. Then what else can we do here? We have you got then k one. Then you end up with, in your mind, just cancel the mass density. You have minus 1/2 k is equal to negative 4 pi g. We'll take the half on the one side. First of all, get rid of the minus and multiply it by -1 again on both sides, and the minuses go away. And so we get 4 pi g. Just stick with me for a second here. You end up 4 pi g on the far right hand side, and you end up with 1/2 k. Well, then just take the 1/2 from the far right hand side and multiply both sides by 2, and you get just k on the right hand side. And multiply 2 on the other side, far left hand side, and 4 pi g becomes 8 pi g. So you get equation 6. K is equal to 8 pi g. Wow! We just used the Newtonian situation to get the final value of k. Now k is, they call it k because it's a constant. So it's always the same throughout Einstein's entire gravitational field equation under all of the situations. So we found k. So now we can write on the bottom here Einstein's full expression with the value of k given its actual true value. Now we're using this balanced units, so c is equal to 1. So that really helps. Then k is equal to actually 8 pi g when you have c is equal to 1, for reasons that we don't have to talk about right now. So there you have it. K is equal to 8 pi g for small mass and low speed approximation converges to Newton. This is great. So we have Einstein's gravitational field expression, just like that, and with k as its actual numerical value. Let's move on. Oh, okay. So where are we? We're here. Let's go down. Okay. Now, let's probe this expression, Einstein's gravitational field expression, with our mind. And we're going to come up with some amazing conclusions from this. Okay, so we start with that. I'm going to go to the next page. There, we start with that at the top. Now, we can operate on this. We think about it. We say, okay, well, this top one is true. And you can if you take G subscript UV times R and put a bracket around it, or just rather, I'm taking just the R and I'm saying R is equal to G superscript UV times G R subscript UV, because the superscript and the subscript, it reduces it. So that's how you take the tensor version, R subscript UV, the covariant tensor, covariant tensor, R subscript UV times G superscript UV, and you multiply those together, you get R. So this equation, this next equation comes straight from the first. Okay. Now it was interesting when you look at the very first equation on the top here. I'm going to grab my handy dandy arrow. Copy me. I'm going to put it on the top. Arrange, move to front. Good. So now I can point here on a hop. So we look here, and we see that R subscript UV is the covariant curvature matrix or tensor, the covariant curvature tensor. Okay, and over here is the R is just the scalar curvature, the Ricci scalar they call it. So you think that this R is going to have less information and have less terms and everything. Well, you look and you say, well, R is equal to G superscript UV times R subscript UV. And then I show in this line right here, I show, well, this is the covariant curvature tensor, and it shows up here the same one. So it has it has the information still right there which is interesting, because it shows that this term actually has these terms. They're kind of buried in there depending on how you look at it. So remember, these expressions are all equal, okay? Arithmetically equal. Okay, so that's an interesting point. And then let's play with it some more. Now all I did here was rather than multiplying G superscript UV times G subscript UV, I just use the associative idea, and I bracket these two terms. So I got the G subscript UV times G superscript UV, which we already know is equal to 4. And so, and the next line I show show it as 4, right? And then negative 1/2 times 4 is equal to negative 2. 1/2 of negative 4 is equal to negative 2. We get this line. And then I have to look at this for a second. Oh, yeah, that's funny. Negative R subscript UV minus 2 R subscript UV is equal to minus 1 R subscript UV. So we get this expression right here. And by the way, this was Einstein's initial choice of the expression, but he abandoned it. So the question is, well, what's wrong with that one? What did Einstein think was wrong with it? So we're going to explore that. And then here we can operate on both sides with the G superscript UV, and then that reduces R to negative blah 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 to the R. And by the way, I got rid of the negative on both sides. I just multiplied both sides by -1, cancel out. So we end up with this. We reduce the scalar the curvature tensor to the scalar tensor for curvature, and we'd also do the same thing with the with the tensor, covariant tensor for stress energy. We multiply by G superscript UV and reduce that to T. Okay, so we have this expression. So all of these expressions are arithmetically the same, okay? And so that is cool. And we have a question. How do we choose, from all these expressions, how do we choose the best one for our model of physical reality that we call the gravitational field equation? How do we make the best choice from all these possibilities, which are arithmetically the same value? So here up in the top I say, let's probe to see if the derivative of r subscript uv is equals 0. The derivative of r subscript equals 0 as is necessary for the conservation of energy. So let's say you're standing on the Earth, and the Earth has a curvature. That curvature is not going to change in time. So the derivative of that curvature should be 0. So what I'm going to operate, I'm going to put it in a form. This is my derivation of it. So like I said before, I'm a design engineer, and I want to design it the way I want to do it. So what I do is I take this 1/2 G subscript UV times R from Einstein's expression, and I'm going to add it to both sides of the equation. So it disappears on this left-hand side, becomes just R subscript UV, because I want to find out if the derivative of that, what it is. So I want to isolate it first. And that's going to be equal to negative pi G times T subscript UV. And then over in this side, since I added on both sides, you get 1/2 G subscript UV times R. Now we know that if I divide, see over here we have 8 pi G times T subscript UV, right? But the R doesn't have 8 pi G times it. Now it's just straight 1/2 G subscript UV times R, right? So I could divide by 8 pi G and then put it in a bracket and multiply it by 8 pi G, okay? And I haven't changed anything. But I'm dividing actually by minus 8 pi G. So that changes the sign here when I do that. So I end up with this expression. Pi G, R, G, V. And when I do that, because we know that R is equal to KT, when I do this, I convert R into T, because I divide it by K, okay? So we end up with this expression. Now, what I'd like, and we have R subscript UV over on this side. And we can take the derivative of both, so I can take the derivative of that, and it's equal to the derivative of the left-hand side is equal to the derivative of the right-hand side. And so we can see if that's equal to 0. So let's do that. And that's what we're going to do next. I say here, let's move this to the front, just in case it isn't. Bring to the front, okay. So let's probe to see if the derivative of R subscript UV equals 0, as is necessary for the conservation of energy. Remember, we're not doing mathematics here, we're doing physics. So we're creating a model of physical reality. We're designing it, and we want to make sure that it has fidelity to physical reality. And part of that is that the curvature tensor, the derivative of the curvature tensor, needs to be equal to 0 to be a good model of physical reality. So we're testing that right now. So we have this expression from our previous chart, the last one we did, at the bottom. And we start with, by the way, in Einstein's meaning of relativity, he also has this expression, so it's a good one. Let's take the derivative of that. So it's equal to 8 pi G times the derivative of t subscript uv. Now the derivative of t subscript, that's the energy density. And like if you think of the Earth, it's not changing its energy density. So the derivative of that has to be equal to 0. So we know that one goes away. And then, so we're left with is equal to 8 pi g times negative 1/2 here times g subscript uv times the derivative of the scalar energy density matrix. So, or tensor, it's the scalar, so it's not a tensor anymore. So we end up with this term. Now, when you do the derivative, of course, the derivative of g subscript uv is equal to 0. It's designed to be that way. So that means that because there's a product here. When you do a derivative of g uv times t, right here, we moved a half out front. Oh, I did it here. That is equal to a half, and then d g uv t and plus g subscript uv, and then dt, because you take the derivative of the first term. If there's a multiplication here, derivative of the first term times the second term plus the first terms times the derivative of the second term. That's how you do derivatives. Well, derivative of g subscript uv is designed to be 0. It's the GV is derivative independent. So that term drops out, and we're left just with this last term here. So it becomes the derivative of r subscript uv is then equal to 8 pi g times negative 1/2 times GV times dt. Now that's the derivative of the scalar energy tensor, which is fine. What we have then is, whoops. See this negative and this negative? And they cancel out, and we get positive 1 times 1/2 g. So this is the result. Okay. So now I can take this and I can throw it over the other side of the expression again. I can, I'm going to add or subtract. I'm going to subtract from both sides of the expression 8 pi g times 1/2 g subscript uv, the derivative of the scalar energy tensor, right? So I do that, and I subtract it from both sides, and on the right-hand side, you get 0 right here. And on the left-hand side, we have this new term that came over when I subtracted it, and which is this term again. Now, we know that this term here, when I multiply this across, this 8 pi g times, which is kt, we know that kt is equal to r. So that becomes r, okay? That becomes r, and there's no 8 pi g anymore. So it's just dr uv minus 1/2 g subscript uv times r is equal to 0. We end up with this expression. Okay. So then we know that this expression here is the derivative of the right-hand side of this thing is equal to 0. So in Einstein's field expression that we derived right here, we derived that earlier. Remember, I'm going to go back and show you. I want to do that. I might get lost. Anyway, you've seen it. I'm not going to do that, I don't think. But you've seen this so many times. This is from Einstein's gravitational field expression, the same one we derived. Okay, on this hand here, and our question was, does this the derivative of this has to equal to 0? And look, we just proved it. Conclusion: the derivative of this is equal to 0. So this expression actually satisfies the conservation of momentum, because the derivative of this expression is equal to 0. So that makes it a good choice for representing physical reality, where you have to have the conservation of energy hold as it holds in physical reality, and that is a part of having that conservation of momentum be satisfied is to have the derivative of the expression equal to 0. Okay, so we just determined that. We proved it, that it is. So let's move on. So the best candidate for the gravitational field expression is what Einstein derived here. Finally, his final choice. And he made that choice because he came to that conclusion. Now Einstein was looking at the left-hand side of the expression, just R subscript UV, and he actually went to mathematicians, and they did and this is what you typically see, page and page and page after page of derivations to show that it's equal to 0. And we just did it very readily. So let's move on. So now what I'm just doing is showing all the expressions we already derived when we were exploring it, the arithmetic expressions. And I want to go over each one of them and evaluate it as for its, just want to get one of these here, get my arrow. Okay, I want to go through each one of them in quickly and just to summarize how good a choice for a physical model is it. These arithmetic expressions, which are all arithmetically equivalent, okay, but not in terms of physically. So let's look at this one. Einstein's first, I said Einstein's first choice was this one. This one is not Einstein's first choice because it's scalar, and it's not a tensor, right? So it says here, scalar expression is a poor model for tensor components, like, for example, the mass, which is mv squared, right? So it's tensor nature, and so this expression is not tensor nature, so get rid of it. Now this one here is Einstein's initial choice, but we just determined that it doesn't satisfy in this form the conservation of energy. So Einstein's initial choice, he realized it later when he had the mathematicians do this derivative of R subscript UV, and it turned out to not satisfy, not be 0. So that's not a good choice. And then we look at this one, and this one also actually, because on this left side, like if you take R subscript UV and it minus 2 R subscript UV, you just get minus R script UV, minus R subscript UV, minus. And so again, the derivative of that is just like if R subscript UV derivative is not 0, then the derivative minus this, then R subscript UV derivative is not equal to 0 either. And so it's a poor model. It doesn't obey the conservation of energy. And this one here, similarly, 1/2 times 4 is -2. So you end up with minus R subscript UV. So it's just a disguised version of it. So the derivative of this is not going to be 0 either in its current form. So that's not a good model, even though it's arithmetically the same. Now, if we look at this expression, the way that the way that the operations are grouped, we still have this here. We know it's equal to 4, and this is r subscript uv. So it's just basically it's the same as this expression. So the order of operations still violates conservation of energy, and that's not a good choice. Now, when you look at this, when you do this order of operations, here we use then this represents r, because it reduces it to r. So this expression here is basically r, and it's basically this expression. So this is the first one that obeys the conservation of energy. You did the derivative of that. That's its meaning. So there's such a subtle transition between these two. It kind of makes your mind ache, but it depends on how you group these operations. And this one up here is Einstein's final choice. It obeys the conservation of energy, and we proved it because its derivative is equal to 0. Great. So we just found out what the best choice, not only what is the arithmetically equivalent choice, but what of that is the best choice for matching physical reality. Because we're doing physics, not just mathematics. And right now I want to take this time to go over what our original objectives were and see how well we met them. First of all, we wanted to expose what job the Jacobian function needed to perform, and then to derive JUV and test to see that it actually works. And we did that, and it did work. Next, we wanted to take the, I gotta put myself on top here. Oh, view, float, I need to float. So next we wanted to expose what job G subscript UV, the metric tensor, needed to perform, and then derive GUV using that specification, and then test it to make sure it's actually doing the job that we designed it to do. And we did that, and yes, GUV did perform that job. Next, we wanted to derive the sort of universal or more general invariant that would function for general relativity. And that's one right here. Derive that s squared, which is the invariant in our local reference frame, is equal to, under all circumstances, this arrangement where you have the metric tensor G subscript UV multiplied by the invariant in the remote location. So you multiply the GUV, which measures, it's a measure of the space-time curvature and other information pertaining to the remote location, and multiply that by the invariant using the dimensions of the remote location, and prove that it equals the invariant that we would have calculate for that in the local in space. So this would all then, since it's always equal to s squared, or what we would calculate in our local frame, then it's a true invariant across all different types of space, whether it has large masses or high speeds. It would still come back and produce, this expression would produce the local invariant. So it's invariant across all of these conditions. And it would also match between portions of space that have curvature of one kind to, let's say you were by Jupiter or something with a large mass. It would convert it to those locations with having curvature. So translate between one form of curvature to another form of curvature. So we derived that and proved that it worked. It wasn't invariant under the conditions of general relativity. Then we needed to get, in preparation for deriving Einstein's gravitational field expression, we needed to show that the metric tensor in the covariant form times the metric tensor in the contravariant form, where UV is a superscript, is equal to 4 for low and high velocity and mass conditions. So it's a general condition. And we looked into that and we proved it as well. Check. Then we wanted to derive the gravitational field expression again. And I say again here because in previous presentations, 1 through 5, we actually did derive the gravitational field expression. But in that situation, purely from looking at the physics and not having certain arithmetic concepts fully developed, but we're still able to do it by pure detective work, and that was a useful exercise. But here we're doing it with the knowledge of the Jacobian J subscript UV, and the knowledge of the metric tensor in greater detail. And so we were able to derive it very easily, knowing this. These two tensors, actually. Sometimes we call them matrices. They're very similar, actually, in meaning. So we derived the metric tensor in full. So check, we did that. Then with JUV and GU subscript UV under our belt, we went ahead and proved, we derived Einstein's field expression, gravitational field expression, and came up with an exact match for what Einstein had recorded in his book from the 1955 revision 5 version of Albert Einstein's The Meaning of Relativity. And so we were able to reproduce it then. And we're also able to go through all of the arithmetically equivalent expressions that we had, and in a way that similar to what Einstein did, looking for which particular expression or expressions were a good model of physical reality, and that they would obey the conservation of energy and of momentum. And we looked for that key quality, which is that the derivative of the left-hand side of the expression equals 0, which is necessary for conservation of momentum. And we found out that we were able to prove in a way, I guess it may perhaps a different way, but got the same result, that R subscript UV minus 1/2 GUV times R is equal to minus 8 pi G times TUV subscript UV, that same expression was a good model. And we understood why Einstein rejected his initial choice, which did not satisfy the conservation of momentum, whereas this expression did solve the conservation of momentum, and we proved it. So check. So through this presentation, looks like we've met all of our objectives, and so basically we can wrap it up at this time as far as we've wanted to go. I think we've achieved it. And with that, I'd just like to say thank you very much for watching this, and I hope you enjoyed it, some fraction of how much I enjoyed making this presentation, and also enjoy perhaps learn as much as I did or more. And I did learn a lot from making this, and it was a very, very good adventure. And I'm certainly not done in science, as you probably already feel and know. When you answer certain questions, it seems like you get 10 more questions. to answer. And so it's a sort of like a hopefully never-ending journey of discovery and exploration and a great adventure. And thank you for sharing this time and this adventure with me. And with that, I'm going to sign off here. And again, thank you very much.